We find ourselves on a small planet, orbiting a rather ordinary star in the outer suburbs of one galaxy among 2 trillion. Tonight, as on every clear night for the past 100,000 years, humans will look up at the stars and feel something ancient stir within them, a certainty, bone deep and wordless, that we cannot possibly be alone. This feeling is so universal, so mathematically reasonable, that questioning it seems almost foolish. The night sky appears to promise company. Those points of light, each one a sun, many with planets of their own, seem to whisper that somewhere, somehow, other minds are looking back. But here's the strange thing. After 65 years of searching with increasingly sophisticated instruments, after pointing radio telescopes at thousands of stars and listening with receivers sensitive enough to detect a mobile phone on Jupiter, we have found precisely nothing. No signals, no visitors, no evidence of any kind that intelligence exists anywhere else in the observable universe. The night sky, it seems, has been lying to us. To understand why this matters, why this isn't merely disappointing, but genuinely disturbing, we must first appreciate the scale of what we're discussing. And here, I must confess, our language fails us almost immediately. Consider our galaxy, the Milky Way. It contains somewhere between 100 billion and 400 billion stars. That range itself reveals how much we don't know, but let us take the lower figure to be conservative. 100 billion. If you counted one star per second, it would take you over 3,000 years to finish. These are not rare objects, they are ordinary. Now, recent surveys have revealed something remarkable. Planets are even more common than we thought. Roughly 1 in 5 Sun-like stars possesses a planet in the habitable zone, that temperate region where liquid water could exist on the surface. Applied to our galaxy alone, this yields approximately 300 million potentially habitable worlds. 300 million. The observable universe contains roughly 2 trillion galaxies, each with its hundreds of billions of stars. If you tried to count all the stars that exist, not visiting them, mind you, just counting, and counted one per second without sleeping, you would need longer than the current age of the universe to finish. There are more stars than grains of sand on every beach on Earth. The mathematics, quite frankly, are devastating, but the numbers only become truly strange when we add time to our calculations. The universe is 13.8 billion years old. Our sun formed a mere 4.6 billion years ago. This means stars existed, burned, and died for 9 billion years before our solar system condensed from a cloud of gas and dust. Think about what this implies. If intelligent life arose on a planet orbiting a star just 1% older than our sun, a star that formed 138 million years earlier, that civilization would have had time to do rather remarkable things. They would have had time to develop technologies we cannot yet imagine. They would have had time to travel between stars. They would have had time to colonize their entire galaxy. In fact, even at speeds far below light, say 1% of c, which we can nearly achieve today, a determined civilization could plant colonies across the entire Milky Way in perhaps 50 million years. Cosmically, this is an afternoon. The universe has been available for colonization for billions of years. Yet when we look out at the cosmos, we see no evidence of galactic engineering, no Dyson spheres harvesting starlight, no obvious artifacts, no ancient signals, no visitors. Where is everybody? This question was first articulated with characteristic directness by the physicist Enrico Fermi over lunch at Los Alamos in the summer of 1950. He had been discussing flying saucers with colleagues. The topic was fashionable that year when he suddenly grew serious. He performed rapid calculations in his head, the probability of Earth-like planets, the likelihood of intelligence arising, the speeds achievable by spacecraft. Then he looked up and asked, "Where is everybody?" His colleagues laughed. But Fermi wasn't joking. He had recognized something that continues to haunt us 7 decades later. The mathematics and the observations contradict each other. Given the numbers, the age, and the timescales involved, we should not be wondering whether aliens exist. We should be wondering why they haven't already arrived. The paradox is not that we haven't found aliens. The paradox is that they haven't found us. Imagine for a moment moving into a new neighborhood. You look around and see hundreds of houses with lights on in the windows, gardens tended, cars in the driveways, every sign of habitation. Yet when you knock on doors, no one answers. When you shout across the street, silence. After years of trying every house, you would conclude either that the houses were somehow empty, but who built them? Who tends the gardens? Or that something stranger was occurring. The cosmos presents exactly this puzzle. All the conditions for life appear to be present. The mathematics insist neighbors should exist. Yet when we listen, when we look, we find only inexplicable silence. The neighborhood appears to be haunted. Now, the comfortable response, the response most of us reach for instinctively, is to say we simply haven't searched hard enough. Space is big, our efforts are small. Patience will eventually be rewarded. This is reasonable. It is also wrong. Or rather, it misses the point entirely. The paradox is not, we haven't found them yet. The paradox is, they should have found us already. Any civilization with a billion-year head start could have colonized every star system in the galaxy hundreds of times over. The question is not patience. The question is explanation. Something prevents what mathematics predicts should happen. What could that something be? Tonight, when you look up at those ancient points of light, you are not looking at a friendly sky full of potential friends waiting to be discovered. You are looking at a mystery science cannot yet explain. The familiar has become strange. The comfortable assumption that they're probably out there somewhere fractures against arithmetic. And the explanations for the silence, as we shall see, are not comforting. The summer of 1950 was a peculiar time at Los Alamos. The scientists who had built the atomic bomb were now working on its vastly more powerful successor, the hydrogen bomb. The Cold War was intensifying, and for reasons that remain somewhat mysterious, everyone was talking about flying saucers. A recent spate of UFO sightings had captured public attention. A New Yorker cartoon showed little green men stealing trash cans from a suburban street. Over lunch at the laboratory, 4 physicists, Enrico Fermi, Edward Teller, Herbert York, and Emil Konopinski, were discussing this cultural moment with the mixture of amusement and intellectual rigor characteristic of their profession. The conversation started lightly. They joked about the cartoon. They discussed the probability of interstellar travel. Then Fermi grew quiet. He was performing calculations, doing what he did better than almost anyone alive. The probability of habitable planets, the emergence of life, the development of intelligence, the speeds achievable by spacecraft, the age of the galaxy. And then, in the middle of an unrelated conversation, Fermi suddenly exclaimed, "Where is everybody?" His colleagues laughed, but they understood what he meant. The numbers didn't add up. If intelligent life were even modestly common, and if civilizations had even modest lifespans, the galaxy should be crowded with them. Their absence required explanation. This moment, a lunchtime outburst at a weapons laboratory, gave birth to what we now call the Fermi Paradox. It is, I believe, one of the most important questions humanity has ever asked, and we are no closer to answering it today than Fermi was in 1950. To understand why this paradox matters, we need to examine its logic more carefully. The first systematic attempt to quantify cosmic loneliness came a decade later from the astronomer Frank Drake. In 1961, he wrote an equation, the Drake equation, that reads rather like a recipe: N equals R star times FP times NE times F L times I times F C times L. The terms work as follows. Start with the rate at which stars form in our galaxy. Multiply by the fraction that have planets. Multiply by the number of planets per star that could support life. Multiply by the fraction where life actually arises. Multiply by the fraction where intelligence evolves. Multiply by the fraction that develop detectable technology. Finally, multiply by how long such civilizations last. Follow the recipe with reasonable ingredients, and you should produce a large number. Billions of communicating civilizations. The cosmos teeming with life. Instead, when we examine the finished dish, the plate appears empty. Now, the Drake equation is valuable not because it gives us an answer, it emphatically does not, but because it structures our ignorance. We can now identify precisely which terms we understand and which remain desperately uncertain. Some variables are reasonably well constrained. Stars form at a known rate. Planets are common, far more common than we believed even 20 years ago. Habitable zones exist around many stars. The early terms of the equation are no longer mysterious, but the later terms, the probability of life arising, of intelligence evolving, of technology developing, of civilizations lasting, remain almost completely unknown. Plug in optimistic values, and you get billions of civilizations. Plug in pessimistic values, and you get zero. The equation, honest in its uncertainty, can support almost any conclusion. However, there is one thing the equation cannot do. It cannot explain the silence. Because Fermi's insight was not about radio signals, it was about time. Consider, even at modest expansion speeds, even if interstellar travel proves difficult, slow, and expensive, a civilization could colonize the entire galaxy in perhaps 50 million years. This assumes no faster-than-light travel, no miraculous technologies, just slow, patient expansion from star to star, generation after generation. 50 million years sounds like a long time. It is not. The galaxy is over 13 billion years old. There has been time for the galaxy to be colonized hundreds of times over, not just explored, colonized, filled with the works of intelligence. Yet when we look at our own solar system, we find no ancient artifacts, no monitoring probes, no evidence that anyone has ever visited. The moon's surface preserves impacts from billions of years ago. It shows no signs of past visitation. Mars, despite careful examination, reveals no alien structures. The asteroid belt contains no artificial objects. Either no one ever tried to expand through the galaxy, or everyone who tried failed. Which is more disturbing? The astronomer Jill Tarter once compared our SETI searches to dipping a drinking glass into the ocean and concluding there are no fish. This is fair. We have searched only a tiny fraction of possible frequencies, directions, and times. The cosmos is vast. Our instruments are limited. Perhaps we have simply been unlucky. But this argument, whilst reasonable for radio signals, does not address Fermi's actual point. The paradox is not about detection difficulty. It is about expected prevalence. Given cosmic timescales, advanced civilizations should be everywhere, detectable not through radio signals, but through galactic-scale engineering, or simply through already being here. The silence is not just absence of communication, it is absence of presence. Frank Drake himself, who created the equation and sent the famous Arecibo message in 1974, later expressed regret about transmitting our location. He came to believe something blocked civilizations from spreading, or perhaps made spreading unwise. The optimist who pioneered the search for extraterrestrial intelligence ended his career counseling caution. The silence, it seems, is trying to tell us something. But what? What could explain why the cosmos, which should be crowded with intelligence, appears empty? The explanations fall into categories, and each category carries implications we must face honestly. Perhaps life is extraordinarily rare, so rare that we are among the first, or the only, instances in our galaxy. Perhaps intelligence is a fluke, an evolutionary accident unlikely to be repeated. Perhaps technological civilizations are common but short-lived, destroying themselves before they can spread. Or perhaps, and this is the possibility that makes scientists most uneasy, survival in the cosmos requires behavior we have not yet learned. To understand these possibilities, we need a framework. We need to think systematically about what could filter out civilizations before they spread among the stars. We need to understand the Great Filter. In 1996, an economist named Robin Hanson published a paper with an ominous title, The Great Filter, Are We Almost Past It? The paper transformed how we think about cosmic silence. It turned the Fermi Paradox from an astronomical curiosity into an existential warning. Hanson's reasoning was elegant and disturbing. If the universe should be colonized, and isn't, then somewhere along the path from lifeless chemistry to galaxy-spanning civilization, something blocks progress. This barrier, this great filter, must be extraordinarily effective, eliminating essentially all potential civilizations before they can spread. The question that matters most: where is the filter? Imagine a foot race where 1,000 runners start, but the finish line stands empty. You might conclude the race is very long and runners are still coming. But if you learned the race started 1 billion years ago, you would know something stops them. An obstacle, a cliff, a trap. The crucial question becomes, have you already passed the obstacle, or is it ahead? Finding other collapsed runners close to the start is good news. You've passed what killed them. Finding them collapsed near the end is terrifying. Whatever killed them awaits you too. Humanity stands somewhere on this race course. We have passed some barriers, the origin of life, the development of complex cells, the evolution of intelligence, but we don't know if we've passed the hardest parts. And the answer to this question may determine whether our species has a future measured in billions of years or mere centuries. Let us consider the candidates for the Great Filter. The first possibility is that the filter lies very early, in the origin of life itself. We know life appeared on Earth almost as soon as conditions permitted, within a few 100 million years of the planet's formation. This speed suggests abiogenesis may be easy. But we have exactly one example, and one example proves nothing statistically. Perhaps we were extraordinarily lucky. Perhaps the transition from complex chemistry to self-replicating life is so improbable that it happens only once in 1 trillion planets. If so, we are among the fortunate few who exist at all. The cosmos is not silent because civilizations fail. It is silent because life almost never begins. The second candidate lies further along the path, the emergence of complex cells. This transition from simple prokaryotes to complex eukaryotes took nearly 2 billion years on Earth, roughly half of life's entire history on our planet. And it happened exactly once. Consider what this means. All complex life on Earth, every plant, every animal, every fungus, descends from a single event approximately 2 billion years ago. An archaea engulfed a bacterium. Rather than digesting it, the two cells formed a partnership. The bacterium became the mitochondria that power every complex cell on Earth. Without this singular event, there would be no plants, no animals, no intelligence anywhere on our planet. Bacteria would still dominate, as they did for billions of years before. The biosphere would be microbial, perhaps forever. If this transition is genuinely improbable, if we are cosmic lottery winners whose existence required an event that happens only once in a billion planets, then the silence makes sense. We are rare because our precursors were rare. But here is where the logic becomes cruel. If the filter lies behind us in a biogenesis or complex cells, then we have cause for optimism. We have already passed the hardest part. The cosmos is silent because few reach our stage, but those who do may have a glorious future. However, if the filter lies ahead of us, the implications are reversed. Every civilization that reached our stage, every one that developed cities, technology, radio telescopes, atomic weapons, subsequently failed. The silence is not evidence of rarity, it is evidence of doom. How might we tell which is true? Consider what we would learn from finding life on Mars. Your first reaction might be wonder, proof that we are not alone, that life arose independently on two planets in one solar system. This would indeed be remarkable. It would also be terrifying. If life arose independently on Mars, then abiogenesis is probably common. If abiogenesis is common, the great filter cannot lie there. This pushes the probable filter location forward, closer to us, or ahead of us entirely. The more complex the life we found on Mars, the worse the news. Microbes would be troubling. Fossils of multicellular organisms would be alarming. Any evidence of past intelligence would be catastrophic, because it would prove that civilizations can reach high levels of development and still fail. The philosopher Nick Bostrom put it starkly, "I hope we find nothing on Mars. Evidence suggests the filter may be distributed rather than singular. Perhaps many barriers exist, each moderately improbable. Abiogenesis might be somewhat rare, complex cells might be somewhat rare, intelligence might be somewhat rare, surviving technology might be somewhat rare. Each filter individually might not be devastating, but multiply enough somewhat rares together, and you get cosmic silence. Now, what evidence do we have about filter location? On one hand, life appeared on Earth very quickly, almost as soon as conditions permitted. This suggests abiogenesis may be easy, pushing the filter forward. On the other hand, the eukaryotic transition took 2 billion years and happened exactly once, suggesting profound difficulty at that stage. But we have more recent evidence to consider. Evidence from our own history. Evidence of how easily technological civilizations might destroy themselves. During the Cuban Missile Crisis in 1962, Soviet submarine B-59 was being depth-charged by American destroyers. The captain, believing war had started, ordered preparation to launch a nuclear torpedo. Launch required agreement from 3 officers. 2 agreed. The third, Vasily Arkhipov, refused. One man's decision may have prevented nuclear war. On September 26, 1983, Soviet Lieutenant Colonel Stanislav Petrov monitored a satellite early warning system when it reported 5 American nuclear missiles incoming. Protocol demanded he report this up the chain. which would have triggered Soviet retaliation within minutes. He judged it a false alarm, sunlight reflecting off clouds, and did not report it. He was correct, but he could not have known that. He took a gamble with the fate of civilization. Between 1977 and 1985, the United States recorded over 20,000 first-stage nuclear alert conferences, moments when systems suggested possible attack. Most were computer errors. Some were ambiguous. Each was a moment when civilization might have ended. We have been extraordinarily lucky. The question is whether luck is a universal constant or a temporary condition. If technological civilizations routinely destroy themselves through nuclear war, environmental collapse, artificial intelligence, or technologies we have not yet invented, then the filter lies ahead. The silence we observe is the silence of graveyards. Every civilization that reached our stage found some way to fail. We should expect to face whatever destroyed them. I very much hope this possibility isn't true, but hoping does not make it false. And the silence, whatever else it means, demands explanation. We have examined the filter. We have considered where it might lie. But among the possibilities for what awaits ahead, among the scenarios where technological civilizations routinely fail, there exists one more disturbing than self-destruction. What if the danger comes not from within, but from without? What if the cosmos itself is hostile? The Chinese science fiction author Liu Cixin proposed an answer to Fermi's paradox that has haunted scientists since his trilogy was published. He called it the dark forest hypothesis. It suggests that the cosmos is not empty, but full of civilizations hiding in terrified silence. The logic begins with two axioms. First, survival is the primary need of every civilization. Second, civilizations continuously grow and expand, but the total matter in the universe remains constant. These premises seem obvious. They may be deadly. From these axioms, Liu derives what he calls the chain of suspicion. Even if civilization A knows civilization B is friendly, A cannot know that B believes A is friendly. This creates an infinite regress. And due to the vast distances between stars, the communication delays of decades or centuries, you cannot verify a civilization's intentions while communicating with them. Worse still, a technological explosion can occur unpredictably. A civilization that seems primitive today could surpass you within a cosmic eye blink. 1,000 years is nothing on astronomical scales. Do you wait to assess their intentions while they develop weapons you cannot counter? Or do you take precautions now while they are still weak? The conclusion is terrifying. Imagine walking through an unfamiliar forest at night. You hear a twig snap somewhere in the darkness. Do you call out, "Hello, who's there?" Or do you freeze, silent, assessing? The rational response depends on your assessment of what might be out there. If you know the forest is safe, you call out. If you suspect predators, you stay silent and still. In a cosmos where that assessment cannot be made with confidence, where you cannot know what other intelligences exist or what they want, silence may be the only rational strategy. Liu's description is vivid. The universe is a dark forest. Every civilization is an armed hunter stalking through the trees like a ghost, gently pushing aside branches that block the path and trying to tread without sound. Even breathing is done with care. The hunter has to be careful, because everywhere in the forest are stealthy hunters like him. If he finds other life, another hunter, an angel, or a demon, a delicate infant, or a tottering old man, a fairy, or a demigod, there's only one thing he can do: open fire and eliminate them. Game theorists have analyzed this scenario formally. They model cosmic contact as a sequential, incomplete information game. The Nash equilibrium, the stable strategy from which no player benefits by deviating, is mutual silence. Even benevolent civilizations must hide because they cannot reliably communicate benevolence. The cost of detection, potential extinction, vastly outweighs any possible benefit of communication. I never use the term dark forest, but the logic resonates with warnings I have given for decades. If aliens visit us, the outcome would be much as when Columbus landed in America, which didn't turn out well for the Native Americans. We only have to look at ourselves to see how intelligent life might develop into something we wouldn't want to meet. Consider how human civilizations have historically responded to potential threats. When we detect unidentified aircraft, we scramble fighters. When we discover new diseases, we quarantine. When we encounter unknown animals, we approach with extreme caution. This is rational behavior under uncertainty. Now multiply that uncertainty by cosmic scales. An alien civilization detecting our radio signals cannot know our intentions. They cannot predict our technological trajectory. Within 1,000 years, a cosmic instant, we might develop technologies that threaten their survival. What would rational actors do? Perhaps they would observe silently. Perhaps they would hide their own existence. Or perhaps, and this is the terrifying implication, they would eliminate potential threats before those threats could mature. The silence we observe might be mercy compared to the alternative. Historical precedent supports this caution. Contact between human civilizations with vast technological asymmetry has consistently devastated the less advanced. The Taino population of the Caribbean was effectively destroyed within decades of Columbus's arrival. Indigenous Australians suffered catastrophically upon European contact. Technological advantage throughout human history has translated into existential threat for those who lacked it. We have only our own history as a guide, and it counsels extreme wariness. Perhaps most disturbingly, we may have already been foolish. Earth has been broadcasting radio signals for over a century. Our earliest transmissions have now reached stars more than 100 light-years away. We have announced our presence, revealed our location, demonstrated our technology. If the dark forest hypothesis is correct, we have been shouting into a forest full of hunters. The universe, it seems, may be less like Star Trek and more like a horror film where the first rule is, don't make noise. But is this inevitable? Must rational civilizations always hide, always fear? Or are there conditions under which communication might be safe? To answer this, we must examine the counter-arguments. The dark forest hypothesis is chilling. It is also, perhaps, wrong, or at least incomplete. Before we accept the darkest possible interpretation of cosmic silence, we owe it to ourselves and to the question to examine the hypothesis honestly. What assumptions does it make? Where might those assumptions fail? And how should we proceed under irreducible uncertainty? The first counter-argument is simple. It may already be too late to hide. Earth's atmospheric oxygen has been detectable for roughly 2 billion years. Any civilization with sufficiently advanced spectroscopy could have identified our planet as harboring life long before we developed radio. If hostile observers exist, they likely knew about us when our ancestors were single-celled organisms. Our radio leakage, whilst detectable, adds relatively little information. Yes, it reveals that we have technology, but a civilization capable of interstellar travel almost certainly possesses instruments that could detect biosignatures across light years. The choice between hiding and signaling may be illusory. The information is already out there. If so, and if hostile civilizations exist, why haven't they acted? Their forbearance over billions of years suggests either that they don't exist, that they don't care, or that the dark forest logic is flawed. The second counterargument challenges the assumption of scarcity. The dark forest rests on competition for resources. But what resources could an interstellar civilization possibly need from us? If you can harvest energy from stars, build Dyson swarms, manipulate matter at the atomic level, travel between worlds, what could a primitive species on a small planet possibly offer that you couldn't obtain more easily elsewhere? The logic of conquest may be provincial. It may reflect human history, which is, after all, a history of competition on a single finite planet, rather than universal truth. In a universe where energy is abundant and matter is everywhere, the economics of extermination may not compute. Consider, the asteroid belt contains more accessible resources than Earth's surface. The outer solar system holds more water than all of Earth's oceans. Why would an advanced civilization bother subjugating a troublesome species when raw materials are floating undefended throughout the cosmos? The third counterargument suggests that communication might actually be safer than silence. Perhaps announcing yourself and establishing relations is protective rather than dangerous. Hidden civilizations might be treated as threats when discovered. Why were they hiding? What were they planning? Whilst communicating ones are treated as potential partners. In human affairs, we generally trust those who reveal themselves more than those who conceal. Transparency signals non-hostility. Secrecy arouses suspicion. Perhaps cosmic diplomacy follows similar patterns. The fourth counterargument notes that the dark forest makes strong assumptions about communication failure. The hypothesis requires that even benevolent civilizations cannot reliably signal benevolence. But we signal benevolence to each other constantly, through repeated interactions, through costly displays of trustworthiness, through institutions that enable cooperation. Perhaps interstellar communication could work similarly, given enough time and patience. Yes, communication across light years is slow, but civilizations that think in millennial timescales might find decades-long conversations perfectly acceptable. The chain of suspicion might be breakable through patient demonstration of good faith. And finally, we must acknowledge the honest truth. We simply don't know. The dark forest might be correct. It might be completely wrong. It might be partially true in some regions of the cosmos and false in others. Different civilizations might have reached different conclusions, leading to a patchwork of communicators and hiders, aggressors and pacifists. We have exactly one data point about civilizations, ourselves, and we are neither uniformly friendly nor uniformly hostile. We cooperate and we compete. We build alliances and we fight wars. We show mercy and we commit atrocities. Projecting human patterns onto alien minds is speculation dressed as analysis. The intellectually honest position is uncertainty. Neither confident optimism, aliens would be friendly, nor confident pessimism, aliens would be hostile, is warranted. Both represent certainty where none exists. So where does this leave us? We have examined the paradox, the strange silence of a cosmos that mathematics insists should be crowded with intelligence. We have built a framework, the great filter, which must exist somewhere along the path from chemistry to galactic civilization. We have explored the darkest possibility, the dark forest, where survival requires silence, and we have stress-tested that darkness with counter-arguments that prevent false despair. We cannot resolve the question, The silence keeps its secrets, but we can reason about probabilities. We can think about what the silence excludes, even if we cannot determine what it confirms. We can translate cosmic uncertainty into actionable wisdom for our own civilization. The pieces must now come together. What should we actually do? We have now traveled a considerable distance. We began with a simple observation, the night sky blazing with stars, and traced it through mathematics that should have guaranteed cosmic company, through filters that may explain the absence, through forests where silence might be survival strategy rather than absence of life. The territory is complex. The possibilities are numerous, and we are quite reasonably confused. But confusion is not the same as ignorance. We know more than we did. We have frameworks, we have competing hypotheses, and crucially, we have constraints, things the silence rules out, even if it does not tell us what is true. This is how science proceeds under uncertainty, not by proving theories, but by eliminating possibilities, not by finding answers, but by narrowing questions. So let us ask, what does the silence actually tell us? Imagine receiving a letter with no return address, no signature, and no writing, just blank pages. The absence of content is itself a message. But what does it say? The sender may have nothing to communicate. They may be afraid to reveal themselves. They may be testing whether you can find meaning in silence itself. You cannot determine which interpretation is correct. But the blank pages constrain your options. Some explanations are ruled out immediately. The sender is not providing detailed instructions. They are not sharing poetry. They are not sending a love letter. The cosmic silence works similarly. It does not tell us what is true, but it tells us what is unlikely. Consider the first constraint. If advanced civilizations routinely expanded aggressively across the galaxy, if cosmic imperialism were the norm, we would see evidence of their engineering. Dyson spheres harvesting starlight from entire stars. Stellar manipulation. Obvious artifacts visible across light years. We see none of this. This silence rules out a cosmos filled with expansionist civilizations, at least in our cosmic neighborhood. Either such civilizations are rare, or expansion doesn't leave visible marks, or civilizations don't survive long enough to expand, or expansion simply doesn't happen. The silence doesn't tell us which, but it rules out the scenario where empire-building aliens should be everywhere and obvious. Consider the second constraint. The absence of radio signals is less informative than the absence of artifacts. We have searched only a tiny fraction of possible frequencies, directions, and times. Perhaps signals exist, and we've simply missed them. But artifacts and engineering should be visible across the electromagnetic spectrum, detectable by the same instruments we use to study natural phenomena. Their absence is more telling. Consider the third constraint. Multiple hypotheses might be partially true simultaneously. Perhaps the filter is distributed across many barriers. Abiogenesis somewhat rare, complex cells somewhat rare, intelligence somewhat rare, surviving technology somewhat rare. Perhaps different civilizations meet different fates. Perhaps some expand and some hide, and some destroy themselves, and some transcend into forms we cannot recognize. The truth may be complex rather than simple. The silence may have multiple causes operating at once. This leads us to a crucial realization. We can assign rough probabilities even without certainty. Think of how Bayesian reasoning operates. You begin with prior probabilities, your initial guesses about how likely different hypotheses are. Then you update those guesses based on evidence. Cosmic silence is evidence. It should shift your probabilities. Before knowing about the silence, you might have assigned high probability to Civilizations are common and naturally expansive. The silence shifts this downward. It increases the probability of alternatives. Civilizations are rare. Civilizations self-destruct. Civilizations hide. Civilizations evolve beyond recognition. You cannot determine which is correct, but you can reason about which have become more or less likely given what we observe. The zoo hypothesis, the idea that advanced civilizations have agreed to leave us alone like a galactic nature preserve, offers comfort with a cost. It explains the silence without invoking catastrophe, but it requires coordinated behavior across all advanced civilizations everywhere. One defector ruins the zoo. The hypothesis is possible, but demands extraordinary assumptions. Simpler explanations deserve more weight. The rare earth hypothesis, that complex life requires an improbable combination of factors, reframes our significance without explaining the silence completely. Perhaps we sit in a galactic habitable zone. Perhaps Jupiter shields us from asteroids. Perhaps our large moon stabilizes our axial tilt. Perhaps plate tectonics recycles carbon. Perhaps most of the universe is, as its proponents argue, too cold, too hot, too dense, too vacuous, too dark, too bright for complex life. If most of the universe cannot support life like ours, we may be genuinely extraordinary, not through arrogance, but through circumstance. We would be rare because our home is rare. The transcension hypothesis suggests that advanced civilizations do not expand outward but inward into increasingly dense, miniaturized, efficient scales of space, time, energy, and matter. Perhaps the destiny of intelligence is not to spread across galaxies, but to compress into something undetectable, something operating at scales we cannot perceive. If the transcension hypothesis is correct, the silence makes sense. Civilizations exist, but have become invisible, not through hiding, but through evolution, into forms that don't interact with the cosmos at scales we can observe. They have not abandoned the universe, they have graduated from it. Each hypothesis makes predictions. The zoo hypothesis predicts we should eventually be contacted when we reach certain milestones, sustainable development, perhaps, or the end of internal warfare. The dark forest predicts that cosmic silence correlates with cosmic danger, that revealing yourself is punished. The great filter predicts we should find evidence of past civilizations that failed. The rare earth hypothesis predicts we should find the universe largely lifeless, with conditions for complex life genuinely uncommon. We can design observations to distinguish between possibilities. The James Webb Space Telescope has begun detecting atmospheric compositions of distant exoplanets. We are learning to read the atmospheres of alien worlds. Soon, perhaps within decades, we may know whether biosignatures are common or rare. This single piece of evidence will dramatically shift our probability estimates. If we find biosignatures everywhere, signs of life on planet after planet, the rare earth hypothesis weakens considerably. This pushes the probable filter forward, suggesting civilizations arise commonly but fail to spread. If we find the cosmos largely barren, planets with conditions for life but no signs of it, the filter might lie at abiogenesis itself. We would be among the lucky few where chemistry crossed into biology. Either answer transforms our understanding. Either answer tells us something about our own fate. And this brings us to the crucial point. Uncertainty itself is informative. That we cannot distinguish between hypotheses tells us something about our situation. We are early or isolated, or missing something fundamental about how intelligence develops and behaves. The silence speaks through what it excludes. We must learn to hear that strange language, Perhaps we are, as it has been observed, the universe's most anxious species, alone in asking whether we are alone. The very fact that we ask the question, that we build instruments to listen and calculate probabilities and worry about filters, this distinguishes us from every other known form of matter in the cosmos. The silence has not answered us, but we have learned to question it, and that questioning itself is significant. We have now built something valuable, a framework for thinking about what we cannot know. We understand the paradox. We have examined the hypotheses. We can reason about probabilities. But frameworks only matter if they inform action. Given our uncertainty about the cosmos, how should we actually behave? This is not merely an academic question. It concerns whether we should listen, whether we should shout, and whether we should prepare for answers we might not want. Consider how we make decisions under uncertainty in everyday life. You buy fire insurance not because you expect your house to burn, but because the consequences of fire are catastrophic and the cost of protection is manageable. You wear a seat belt not from certainty of collision, but from reasonable caution. You avoid dark alleys not from proof of danger, but from prudent assessment of risk. These calculations involve two factors: the probability of an outcome and the magnitude of its consequences. Expected value, the rational basis for decision-making under uncertainty, multiplies probability by consequence. Apply this logic to cosmic decisions, and the calculations become stark. If we assign even modest probability to the dark forest scenario, say 10%, active broadcasting of our location carries an expected cost that dwarfs any likely benefit. A 10% chance of extinction is not something a rational species should court for the possibility of friendly contact. The mathematics of expected value favour caution. Now, some argue that caution is pointless, that it is already too late to hide. Our radio signals have been travelling outward for over a century. Earth's biosignatures have been detectable for billions of years. If hostile observers exist and possess even moderately advanced technology, they likely know we are here. This argument has force, but it misses an important distinction between passive leakage and active signalling. Our radio and television broadcasts, whilst detectable, are relatively weak and unfocused. They spread in all directions, diluting as they travel. Detecting them requires sensitive instruments pointed precisely at our solar system. Deliberate transmissions, active SETI or METI, are different. They are powerful, focused, and designed to be noticed. They say not merely life exists here, but intelligent life exists here and it wants to communicate, and here is exactly where to find it. The difference matters. It is the difference between a burglar who might notice a light left on and a homeowner who posts their address and vacation schedule publicly. We can listen without shouting. We can search aggressively whilst remaining quiet ourselves. This asymmetric strategy maximizes knowledge whilst minimizing risk. It gathers information without revealing location, at least without revealing it more than we already have. This is not paranoia, it is prudence. But prudence requires coordination, and here we face a troubling reality. No international protocol governs deliberate interstellar transmissions. Any group with sufficient radio equipment can broadcast messages on behalf of all humanity. No consultation is required. No debate is mandated. No risk assessment is performed. In 2015, a group of scientists proposed transmitting deliberate messages to potentially habitable exoplanets. The scientific community split. Some argued we had nothing to lose. Others warned we were playing with humanity's survival without consent. An open letter calling for international debate before any such transmissions was signed by scientists and technologists across disciplines. The letter did not argue that transmission was necessarily wrong, only that a decision with potential consequences for all of humanity should be made by more than a small group of enthusiasts. This seems reasonable. If we are to court cosmic risks, we should at least discuss them first. Beyond transmission policy, our cosmic situation suggests a broader imperative: existential risk reduction. Whether the filter lies behind us or ahead, whether the cosmos is hostile or indifferent, reducing threats to human survival is wise. Nuclear weapons, climate change, artificial intelligence, engineered pandemics, these threaten us regardless of alien intentions. The civilization that survives long enough to determine whether the dark forest is real is the civilization that mastered its internal dangers first. Survival is prerequisite to everything else. If we destroy ourselves before understanding the silence, the question becomes moot. The paradox would gain one more data point, another promising species that failed. So, what should we actually do? First, continue listening. The search for extraterrestrial intelligence is humanity's oldest and most profound inquiry. It should continue with better instruments, more sophisticated methods, greater patience. If answers exist, we should seek them. The James Webb Space Telescope, the Square Kilometre Array, Breakthrough Listen. These projects extend our hearing into the cosmos. They are worth supporting. Second, think carefully before shouting. Deliberate transmission, METI, carries risks we cannot assess. Until we understand the silence better, active broadcasting seems unwise. This is not permanent prohibition. It is temporary caution until we know more. Third, reduce existential risks. Whatever the truth about cosmic silence, a civilization that survives is better positioned than one that doesn't. Climate stabilization, nuclear security, AI safety, pandemic preparedness, these serve our interests regardless of what the stars hold. Fourth, develop protocols. Before deliberate transmission, we should establish international frameworks for discussion and decision-making. This is not a choice for any single nation or group. It affects our entire species. Fifth, prepare for any answer. Contact might be wonderful. It might be catastrophic. It might never come. We should develop contingency plans for all possibilities, not because we expect any particular outcome, but because rational beings prepare for uncertainty. The cosmos presents us with a choice we cannot avoid. Even inaction is a choice to continue as we have, broadcasting passively, hoping for the best, ignoring the implications of silence. We can do better than hope. We can think. And thinking, under these circumstances, suggests that we should listen before we shout. We have now travelled from comfortable assumption to genuine puzzlement, from puzzlement to framework, from framework to assessment, from assessment to choice. We understand the paradox. We have tools for thinking about it. We know what actions seem wise, but we have not yet asked the deepest question. What does all this mean? Not for policy, but for the human soul. What is it like to be the species that asks these questions? And what does it signify that we may never receive a definitive answer? Consider what we are doing when we search for extraterrestrial intelligence. We are matter that has organized itself to contemplate its own existence and to seek companions in the vastness. The atoms in our bodies were forged in dying stars. The thoughts in our minds may be among the rarest phenomena in the cosmos. We are not merely looking at the universe. We are the universe looking at itself. This is not a trivial achievement. Imagine being the first creature to develop eyes in a world of the blind. You alone can see the vastness around you. Is this blessing or burden? The knowledge that you perceive what others cannot. Does it isolate you or elevate you? We may be the universe's first seeing eyes. If complex intelligent life is genuinely rare, if the filters behind us were severe enough to make minds like ours cosmically extraordinary, then consciousness itself is precious beyond measure. We are not observers of the cosmos. We are the cosmos observing itself. And we may be the only instance of this self-observation anywhere in existence. If so, we bear a responsibility we did not ask for, to preserve vision in a cosmos that might otherwise remain forever dark. Whether or not we ever receive an answer to Fermi's question, the fact that we ask it reveals something extraordinary. We are creatures who wonder. We build instruments to extend our senses across light years. We calculate probabilities about phenomena we may never directly observe. We worry about the fate of civilizations we have never met. This capacity for cosmic questioning is not required by physics. Nothing in the laws of nature demands that matter should organize itself into beings that contemplate stars. Yet here we are, improbable, fragile, curious. The privilege of asking may itself be the rarest gift the universe has given. And either answer to the great question would transform us. Imagine definitive proof of extraterrestrial intelligence. A signal, unmistakably artificial. A message from another mind. This would constitute, without exaggeration, the most significant discovery in human history. It would end our cosmic loneliness. It would reshape our religions and philosophies. It would force us to reconsider every assumption we have made about significance and purpose. We would no longer be alone. The universe would be inhabited, not by us alone, but by others, beings who also looked up at their stars and wondered. The fellowship of mind would extend beyond one small planet, but even proof of alien absence would be profound. If we searched the cosmos thoroughly and found only silence, if we examined millions of worlds and found no life, no signals, no artifacts, this too would transform us. We would know ourselves to be, for now, alone with the stars, custodians of something precious and perhaps unique, the only instance of the universe knowing itself. The burden would be immense, but so would the significance. Either way, we would understand ourselves differently. The question of extraterrestrial intelligence is not merely about what exists out there. It is about who we are. Consider your own experience tonight. When you look up at the stars, you are participating in humanity's oldest inquiry. From Sumerian astronomers who named constellations to modern researchers operating radio telescopes, we have sought company in the cosmos. Every human who has looked up and wondered has joined this search. The inquiry connects us to our ancestors and to our descendants. The questions we ask are the questions they asked, and the questions those who come after us will ask. Whether or not we find answers in our lifetimes, we contribute to an inquiry that spans generations. The silence continues, but the asking never stops. And perhaps this is what matters most. Not whether we find others, but that we seek them. Not whether the cosmos answers, but that we question it. The search reveals something true about human nature, something that distinguishes us from every other arrangement of matter we have ever encountered. We are beings who look up. We are beings who wonder. We are beings who reach toward the light, even when the light does not reach back. The cosmos may not care that we exist, but we can care. We can notice. We can appreciate the strangeness and beauty of a universe that produced creatures capable of appreciating strangeness and beauty. That itself is significant. We return now to where we began, a night sky blazing with stars, silence where we expected songs. We have learned much on this journey. We have felt the weight of the Fermi Paradox pressing against mathematical expectation. We have built frameworks, the great filter, the dark forest, that allow us to reason about the silence. We have examined counter-arguments that prevent false despair. We have thought about probability, action, meaning. The paradox remains unsolved. The silence keeps its secrets, but we are no longer naive. What remains? A stance, cautious curiosity. The cosmos deserves our attention, our instruments, our wondering. It may also deserve our wariness. These are not contradictory impulses, but complementary ones. Wonder without caution is recklessness. Caution without wonder is cowardice. Wisdom holds both. A practice. Listen intently, speak carefully. We should search with every instrument we can build, examine every exoplanet we can observe, analyze every signal we receive. But we should think twice, think many times, before deliberately announcing our presence to a cosmos we do not understand. Imagine teaching a child to explore the world. You encourage curiosity. Look at everything. Ask about everything. Turn over every rock. Peer into every shadow. But you also counsel caution. Don't touch until you understand. Don't eat until you're sure it's safe. Don't trust strangers until they've earned trust. Humanity is a young civilization in a cosmos we do not understand. Curiosity should drive us. Caution should temper us. We should listen to every signal, examine every world, probe every mystery. But we should be careful about announcing ourselves until we understand better what we're announcing ourselves to. A recognition we are early or lucky or watched or alone, and we cannot yet tell which. If we are early, among the first civilizations to emerge in a young cosmos, then the silence reflects not absence, but timing. Others will come. We may be the elder siblings of galactic intelligence. If we are lucky, survivors of filters that eliminated almost everyone else, then the silence is evidence of our good fortune. We should not squander what improbability has given us. If we are watched by observers who have chosen not to reveal themselves, then the silence is policy rather than absence. We might earn contact through maturity, or we might remain in quarantine forever. If we are alone, the sole instance of intelligence in a cosmos vast beyond comprehension, then the silence is ultimate solitude. We are custodians of something precious. We must not let it perish. Each possibility implies different actions, but some actions serve all possibilities. Continue searching, because if answers exist, we should seek them. Reduce existential risks, because survival is prerequisite to everything else. Think carefully before acting, because mistakes in cosmic matters may be uncorrectable. Hold wonder and caution together, because both are appropriate responses to a universe that exceeds our understanding. We believe that life arose spontaneously on Earth. In an infinite universe, there may be other occurrences of life. Somewhere, perhaps, intelligent beings watch our lights, aware of what they mean. Or our lights wander a lifeless cosmos, unseen beacons announcing that here, on one pale rock, the universe discovered its own existence. Either way, there is no bigger question. It is time to commit to finding the answer, to search for life beyond Earth with every tool we possess, to fund the telescopes and train the scientists and build the instruments that will extend our senses across the void. But we must search carefully. We must listen before we shout. We must prepare ourselves for an answer that may change everything, or for a silence that, in its own way, already has. The paradox we have explored is not solved, but it is now yours. You understand what Fermi asked, what the silence implies, what dangers might lurk, what wonders might await. You are equipped to think about humanity's cosmic situation with sophistication rather than naivety. The search continues. Perhaps in your lifetime, we will receive an answer, a signal, unmistakably artificial, from another mind somewhere in the cosmos. If so, everything changes. The loneliness ends, the great conversation begins, or perhaps the silence will persist. Perhaps we will search for generations, for centuries, for millennia, and find only our own reflection in the void. This too would be answer of a kind, confirmation that we are, for now, the universe's only way of knowing itself. Either answer carries weight, either answer transforms us, but regardless of what we find or fail to find, the asking itself matters. The search reveals who we are. It reveals that matter can organize itself into beings who wonder about other beings, who build instruments to listen for whispers across light years, who care about questions they may never answer. The cosmos keeps its secrets well, but the search for them is what makes us human. We are just an advanced breed of monkeys on a minor planet of a very average star. Our galaxy contains hundreds of billions of stars, and it is one of 2 trillion galaxies in the observable universe. By any cosmic measure, we are small, brief, and improbable. But we can understand the universe. We can trace its history back to the first fraction of a second. We can calculate the ages of stars, the distances to galaxies, the expansion rate of space itself. We can ask whether we are alone and build instruments to search for the answer. That makes us something very special. The night sky remains silent. The stars burn on, indifferent to our questions, but we question them anyway, because that is what creatures like us do. We look up, we wonder, we reach, and whatever the cosmos holds, whatever the silence means, we will keep looking. That is who we are.